Hey all, this is Derek, and this is section 2.4, and it's going to be an introduction to the difference quotient. This idea actually ends up being all first quarter calculus. If you throw a limit in front of that, that becomes the definition of a derivative. So this will show up again and again. Today we're just going to look at it in like the case of a line, which is about the least interesting version there is. And we're going to see it's just going to be slope again, much like average rate of change and much like 2.1 where we did slope. But it's going to grow into other things as math goes on. So take today as a meet and greet, and it's also really good practice with function notation. So if you remember from the last section, average rate of change was this f of b minus f of a over b minus a. And I had a drawing kind of similar to this that I did. And this would have been our f of b, and this would have been our f of a. And this, so we're finding our change in y. This was our b, this was our a, we're finding our change in x. So the difference quotient is the same thing again. So here we're putting, at this point, we're putting in x and we're getting out f of x. And then this distance h, let me write it a little bit bigger. So we're going from wherever this is, some distance h over to here, which makes x plus h. And then when we put that in, what we get out is f of x plus h. So if I go f of, well, basically y2 minus y1, it's f of x plus h minus f of x, which is right there. And then over x2 minus x1, a change in x plus h minus x, the x's cancel, and there you have the over h. So this, and then that slope formula back in 2-1, they are all finding the slope of this line that we're looking at. It's just we're looking at several different notations. And then the things that you end up doing with it ends up being different for sure, but they are all kind of looking at the same thing, which is slope. Okay, so this first example, they are using a instead of x. It's actually leading to the exact same place. In my notes, I have it f of x plus h. They're just going to do an a plus h, same thing. So f of a, what they're doing with this is showing that we can do a variable change. And so if my function is right here, f of x equals 3x plus 7, finding f of a literally just means changing that x to an a and saying it's just going to be some value a instead of the general x. If I want to find f of a plus h, all of this right here is going in for that x. Because remember, the same way if we found f of 7, we go 3 times 7, the 7 goes in for the x. Here, a plus h goes in. So this would equal 3, and then need the parenthesis, a plus h, and then plus 7. And then we could distribute that 3, and then that's going to come out 3a plus 3h plus 7. So that would be that one. And then part C of this is putting these two things together and putting it over h. So what they're having you do is evaluate the two pieces of the difference quotient, and then put it all together in the problem. In the next one, it'll just be do the difference quotient, do this. So here, we're going to go f of a plus h, that was this expression. So 3a plus 3h plus 7 minus f of a, that's this, 3a plus 7. Those parentheses totally important, otherwise the 7s end up not canceling, and that ends up being a bummer. And then all this is over h. So then if I distribute that sign, so minus 3a and then minus 7. Something that should happen when you do the difference quotient is that the stuff in the parentheses here, the f of a or f of x in my notes, it should cancel. So I got a plus 7, I got a minus 7, I got a minus 3a, I got a plus 3a. So then what's left is 3h over h. H is canceled, that should also happen. And we end up that the difference quotient is 3, which remember back here, we were saying the difference quotient is the slope, and the slope of that line is 3, so I really should come up with 3 on this. You know, I should always get the slope, assuming we're doing something linear. And this is the only chapter we do something linear. After this, it's curves, and it's much more meaningful. One more example with just kind of straight away setting up the difference quotient. That'll be it. Okay, so for this one, we're asked to, given this function, evaluate and simplify the difference quotient. So here's our difference quotient. So we're going to go we want to find f of x plus h first. So that's going to be negative 5x plus h minus 1. So that is f of x plus h. And then next we subtract f of x, which is just the original function, so minus, and that all-important parenthesis, negative 5x minus 1, and close that. And then that's all over h. And I'll just abbreviate this difference quotient. So then next we'll distribute some stuff. So let's go negative 5x, negative 5h minus 1. Minus and minus, that's going to be a plus 5x. Minus and minus again, it's going to be a plus 1 all over h. So then again, if I did this right, all this stuff should cancel. If not, my signs are probably wonky. So plus and minus is good. Plus 1 minus 1 is good. And then if we look at what's left, it's minus 5h over h. H over h is 1 for all values other than 0. And that was a thing in the difference quotient. H can't be 0 until it's a limit. And that gets us negative 5. And what should it be? It should be negative 5, right? Because our slope was negative 5. So we just kind of took the longest road ever to say, yeah, slope's negative 5. Again, far more interesting when we get to functions that have curves rather than just straight lines.